Okay, so e to the u is just e to the u times u prime as a derivative. Integral of e to the u is just e to the u plus c. Now, first semester, we also learned about exponential functions that's not base e. So a to the u could be like, 2 to the x or 3 to the x. Examples could be like, 4 to the x, 9 to the x. Right? These are all exponential functions that have bases other than e, but they all kind of follow the similar rule. So we just organize it as just a to the u. Okay, so the rule for a to the u looks a lot like e to the u, except for the fact that it's not base e, so there's a little conversion that has to happen, and that conversion comes in the form of natural log of a. And then once you get past that conversion, then your rule looks a lot like e to the u. E to the u is just the original function times the exponent's derivative. So a to the u is also that as well. The original function times the exponent's derivative. Let me just do a quick example here. Let's say I want to find the derivative for 9 to the 3x. Okay. This is base 9. Base 9 is it's an exponential function because it's a constant raised to a variable. So it falls under this category of a to the u. Okay. We follow the rule here. So natural log of a, my a value is what? 9. Yeah, that's my base. So natural log of 9. And then the rest of it looks like e to the u. It's just the original function times the exponent's derivative. Okay, it's a little messy because none of this can merge together. The natural log of 9 and 9 to 3x and 3, these are all kind of in a separate place. So, we can rearrange it, but all of this has to stay. Okay, so that's what we did first semester, right, with derivative rule for a to the u. Now, integral of a to the u. Imagine you're on this side of the rule, and you're trying to make your way back to the left side. So if I start off with a to the u du, think of u prime as basically a du here. I'm just basically back to a to the u, but something has to happen with this natural log of a. It's going to end up being divided over. And if it's divided over, it's going to be in the denominator. So the integral of a to the u is just a to the u with a little coefficient of 1 over natural log of a in front. So that's why the antiderivative for a to the u has a natural log of a that lives in the denominator, and then the rest of it is just a to the u plus c. So if you look, it resembles the integral of a to the u, very much the same thing. But again, a conversion has to happen with a natural log of a. We're going backwards, and that's why the natural log of a ends up in the denominator this time. Okay. Remember that natural log of a is just a constant. We can have it pushed out in front if we're trying to deal with the integral rule. Okay, it's not a variable. So 2 to the x dx, you see that this matches nicely with our a to the u rule. You can go through u substitution, but the u is just the x, so there's not going to be any leftover value we have to keep track of. We can jump directly into this rule and just replace the a with what? 2, yeah. And so just 1 over natural log of 2 times 2 to the x plus c. Nothing to keep track of, no coefficients that's left over, that x won't produce anything except 1. Keep in mind that this 2 is not really 2 like you would expect 2 to be. Okay, this is stuck to that exponential form, so if I see any other coefficient, I can't do a number times that 2 and clean it up. So this 2 is kind of a standalone thing. It's not easily merged with anything else. Okay. All right, example 2. Very similar format, right? We see that a to the u, that exponential function, 3 raised to the 4x. But this time we got to go through u substitution, right? What's our u value? 4x, okay. Now I do want to talk a little bit of a shortcut for u value that are relatively simple. And what I mean by simple is if it's like a linear function. If your u value is like 4x or 8x or 2x, there's a little bit of a shortcut that can help you avoid as much writing if you choose to. But let's discover that at the end. Okay, let's go through the full u substitution process. And if you can see the pattern later, and if you want to apply that pattern and avoid having to write as much stuff down, you're welcome to do that. Okay, so let's say our u value is 4x. du over dx is 4. Cross multiply. dx equals du over 4. Make our substitution. Okay, all the x's goes away, but there's a leftover coefficient of what? Good, 1/4, right? It's not 3/4, right? That 3 is stuck as part of the exponential function. It's the 1/4 that comes out in front. Okay, that 1/4, you can cover up that 1/4, and the rest of it matches nicely with the rule that we want to apply. So we just jump into it, right? 1 over natural log of a. What's my a value? 3. Okay, so the 1/4 stays. 1 over natural log of 3 times 3 to the u plus c. Replace the u back in terms of x. Now, once you get to your antiderivative and you replace the u in terms of x, it really doesn't matter how you present it. You can have it as separate fractions and just replace that with 4x. You can have it kind of partial fraction and something in front, or you can have it all as one fraction. It really doesn't matter. Okay, so there's not going to be a standard way of writing your answer. College Board accepts any variation as long as all the pieces are there. Okay. So the shortcut that I want to talk about is look at the u value and look at what comes out of that u value. Can you come up with a pattern or rule that can be applied for any relatively easy u value that's a linear term? Yeah, okay. Okay, it's just basically the reciprocal of your derivative, right? So 4x will be 4, and just take the reciprocal of that times 1/4. Okay, it's kind of like the opposite of chain rule, right? Chain rule is just, like e to the u times u prime, right? If it's e to the 4x, it'll be e to the 4x times 4. Imagine just going through that process, but you're undoing a chain rule, but then it's the reciprocal of that because you're undoing that process. So that's why there's that 1/4. So it's just always the reciprocal. So as soon as you can find that derivative, you just flip that derivative and you just write that as a coefficient. So if you want to skip this process of writing out every little step and jump from here to here, you're welcome to do that. But that's only if you're comfortable either now or later, but you don't have to. Okay, just want to kind of give some time-saving features, especially if imagine a problem that has multiple u substitutions to it, and rather than have to work out every part, if you just know the pattern, you can move through the problem a little faster. Okay. Now, I wouldn't suggest it for anything that is more complicated than a linear u value. I would go through and work through the whole process if it's anything more complex. Okay, number 3. Okay, we observe this problem. This is too complex for any one rule to manage. We got to go through u substitution. Okay, what could be our u value? 10x. Okay. Okay, that secant squared x is helpful to see because we know that the derivative of tangent is secant squared, so that process should remove that secant squared down the road. Okay, make our substitution. What do you see? Yeah, secant squared x goes away. No coefficients to keep track of. This is just basically an a to the u rule, right? Just follow whatever the a to the u rule says. 1 over natural log of 5 times 5 to the u plus c, and then bring the u back, or bring the x back into the answer. Okay, example 4, too messy for one rule to manage. We got to go through u substitution again. Can you guess as to what the u value could be for number 4? Yeah, the entire exponent. That exponent 3 minus x squared is helpful because we know that derivative should produce something that is some variation of that 3 minus x. So we're hoping that 3 minus x can go away with this process. Okay, so u equals 3 minus x squared. Now to find the derivative, this is something from first semester. You guys remember what process is involved with this type of setup? Chain rule. Yeah, this is outside function and inside function, right? Outside derivative times inside derivative, chain rule. So remember, outside portion is that parentheses squared. The inside is that 3 minus x. And we're just taking turns with their derivatives and placing them next to each other. Okay, what's parentheses squared's derivative? To the first power. Okay. And then what's the inside portion's derivative? -1. And then fill the parentheses with the original parentheses. Okay. That 3 minus x is helpful because we know that, okay, that 3 minus x should hopefully handle this 3 minus x that we're leaving out. Okay, cross multiply. Make your substitutions. All right, what do you see here? Coefficient of, good, -1/2. Okay, make sure that you don't push the 7 out as well. The 7 is not a coefficient, it's part of the exponential function. Okay, matches nicely with my a to the u rule. Again, any variation of this answer, if you want to rearrange your fraction differently, that's perfectly fine. There's no, as long as all the pieces are there, that's what's important. Okay, number 5, you see how much more complex number 5 looks? So usually the general rule of thumb is the more complex the problem, the bigger your problem is, the larger your u value has to be, right? In order to cancel out the remaining portions. So so keeping that in mind, what could be a potential u value that will allow the derivative to take out the rest of the x's in the problem?
2x squared minus 5.
So the problem is with that is that 2x squared minus 5 will handle this x, but then you're left with 7 to the u over 5 minus 7 to the u. And we don't have a rule that can handle an a to the u over an a to the u. And yeah, entire denominator, right? So it's okay to initially pick the wrong u value, but the hope is that you can kind of picture that u value and imagine, wait, is that going to make my problem simple enough where it's actually going to look like one of these rules, right? Because we're so restrictive with our integral rules that if it doesn't look exactly like this, even if it looks like a variation of this, it's just, there's no match. So the hope is that, okay, if that entire denominator can be the u value, then the derivative of this should hopefully handle this rest of the mess that we have here. So as a reminder, we have a rule for the derivative for a to the u, which is natural log of a times a to the u times u prime. So let me write that rule here so we can have it in front of us.
So the u is the entire denominator?
Yeah, entire denominator, right. Okay, so here's my u value. U equals 5 minus 7 to the 2x squared minus 5. Du dx, we know the 5 goes away to 0. The negative, think of that as a -1. All right, so -1 is going to stay, and then we jump into our rule. 7 is our base a, so natural log of 7 times the original function times the exponent's derivative. So 2x squared minus 5 becomes what? 4x. Okay, that's a big mess here, but we do need this because we want a lot of things to go away, to pair and match up, right? So cross multiply here. So I'm just going to replace what I have underlined, and everything else I'm just going to copy it back into my problem and see if things will go away nicely. Okay, what do you guys see here? Good, right? So that's a big part that we definitely needed to go away. What else? Yeah, 2x and 4x. I think we can deal with the 2 and -4 later, but the important thing is that the x's go away, right? That's important. Everything else is okay because those are just coefficients that we can push out in front. Okay, so what can I push out in front? Okay. Yeah, so the 2 and 4, I'm just looking to reduce that to be -1/2, and then the natural log of 7 can go along with it. So this is what I have. So a lot of things cleans up nicely. The coefficients, we merge them together, but it's okay to have natural log involved as long as there's no variables here. So if you cover that up, that's a nice rule, right? We have a rule for that. That's natural log. Sorry? How's the I put the you can put negative above or below. Where did the -4 come from?
Oh, I see.
From the very beginning, yeah. So I had that -1 in front of that 7, and I just carry that over all the way to the end. Okay, so natural log of u plus c, I'm just going to skip that process and replace the u back in terms of x with my next step. Okay. Any questions with 5? Okay, take a look at number 6. Again, if you see definite integrals, we have to keep reminding ourselves that it's the last thing that we do, right? We never want to involve the bounds with the problem of AC in front of you. Okay, you got to take care of the indefinite integral before that negative 12 and 6 can even play a role in the problem. So I'm just going to force myself to rewrite the problem without the definite integral and then just focus on the problem at hand. What's another way that I can rewrite x over 3 to make more, yeah, 1/3 x. I feel like students have an easier time with 1/3 x. It just feels more natural for our derivative process. Okay, so this should be a relatively easy setup here. What's our u value? The 1/3 x. Okay, I'm going to go through the full u substitution process, but we should be able to look at this and tell what coefficient is going to come out of that process. Okay, that's the derivative, but what is going to be left over if we were to skip the u substitution process? 3, yeah, it's the reciprocal of the derivative. Okay, now you don't have to go through this. You don't have to go through that shortcut method, but I just want to kind of show you that we can save a little bit of time for these easier, simpler u value. So you see that the 1/3 x will just produce a 3 out in front, right? So you find the derivative and you flip it, and that's always just going to be the leftover. Okay, so now we can apply the antiderivative. 4 to the u is just 1 over natural log of 4 times 4 to the x over 3. Okay, I will bring the u back into the, well, I'll bring the x 1/3 x back into the answer, and then I can involve the negative 12 and 6. Okay, any questions up to this point? We found the antiderivative. Instead of the plus c, I'm going to be involving my bounds. Okay, I have some students from first period asking, wait, do I have to flip the bounds because the bounds are out of order? Again, I will say that if you're dealing with a graph and you're trying to put something onto a graph, typically you like to read from left to right. But I would say it's not worth the trouble here because this process will just take care of the answer for you. Okay, whatever answer is going to come out, it'll be the same as if you flip the bounds and change the sign. So I would say don't worry about the order of the bounds. Just work it out the way it's supposed to be, and your answer will work itself out. Okay, I don't think it's worth the trouble to flip the bounds if you're not having to do a visual component to your problem. Okay, so upper bound first. Plug negative 12 in for x. I get negative 12 over 3, which is negative 4. Okay, minus, now I'll do the lower bound. One-third times 6 is 2. So this is messy, but there's not much that we can do to combine them. So also, you won't get penalized if you have your answer in front of you and it's not cleaned up. So not on the quiz, no. Okay, so any variation of this answer is fine. Some students decide they want to pull a common factor out in front. But I would say generally on the AP exam, for instance, if you get to this point, just go ahead and stop because the more you try to clean up, the more you're introducing a potential error. And if you have the right answer already, just move on to the next problem. Okay, any questions, first page? Now, the second page is just more practice problems. I'd like to just move into our quiz review. Is anybody still needing this? Okay, I'll hold on a second. Okay, everybody good? Okay, so we're going to skip page 6. 7 is just a list of rules, integral and derivative rules that we've learned up to this point. Page 8 is spelling out each of the, it's a checklist, kind of going down your integration rules. So first thing you want to do is check for power rule. If it doesn't work, then use substitution. If it doesn't work, then change your variable. And then finally, long divisions. The division is the specific example where your numerator is higher than the denominator and there's more than one term in the denominator. Okay. But let's go to page 9 and let's start the quiz review sheet here. Okay, I like to start at the very top and just start going over some of the rules that we're going to have to be able to memorize for the quiz. So these are the major ones and also the new ones here. So this is first one is just power rule, right? U to the n. It's just u to the n plus 1 over n plus 1 plus c. All right, we add 1 to the exponent divided by the new exponent. 1 over u. This is the exception to the power rule. If it's u to the first power in the denominator, we have natural log to handle this rule. E to the u is just e to the u. Now we have 6 trig rules that we learned from first that are just carryovers from first semester, right, going backwards. But these are specific rules that are additional ones that involve natural log. So the way that I remember them is I think of tangent in terms of, okay, what's tangent in terms of sine and cosine? I know that tangent is sine over cosine. And we learned about how, well, if I think of it as sine over cosine, if I go to use substitution, I'm going to target the denominator. So that's what shows up in the rule. It's natural log of cosine of u plus c, but cosine produces a negative derivative. So that's why there's a negative in my antiderivative. Okay, so that's how I remember the tangent rule. Cotangent, it doesn't show up as my original 6 integral trig rules, but I can think of cotangent. I know cotangent is going to be one of the natural log rules. I think of cotangent as cosine over sine. And if I target that denominator as my u value, if I were to solve it the way that we did as a way of deriving this rule, that sign is going to show up in the rule. Okay, it's going to be natural log of sine of u plus c. Sine produces a positive derivative, so that's why there's no negative in the antiderivative. So it's just going to be positive natural log absolute value of sine of u plus c. A lot of times what trips students up here is the negative and positive, because these are not trig functions that we normally associate with negatives and positives. So tangent, we always associate tangent with positive, but in this case, it's going to be negative. Cotangent, we usually associate that with negative, but in this case, it's going to be positive. So just be aware that this throws off a lot of students, the signs. Okay, secant. We didn't derive the rule for secant. We just jump into memorizing them. So secant also involves natural log, but it involves trig functions that you would normally associate with secant. So secant's derivative is secant tangent. So those trig functions show up again, but instead of multiplying, they're being added. Cosecant has a similar pattern. Cosecant, we associate cosecant and cotangent for cosecant. So it has a similar form. It's just cosecant plus cotangent, and then negative in front. Secant we associate with positive, cosecant we associate with negative, so that still stands. It's just this, the signs here really throw students off. So just put a star next to them, understand that those are easily easy ones to miss. Okay, a to the u, we just learned this rule. Looks a lot like e to the u, but there's a coefficient balancing term in front, and then a to the u plus c. Okay, so what I want to do with the first page is we're not going to work through the entirety of every problem. I just want us to identify the first step. I think the first step is the hardest part, right? Getting to that first, because once you get that first step, then everything else is kind of, it's just kind of like the same process through. So look at number 1. Hey, we always want to go down our checklist, right? Can I do power rule? But there's too many terms in the denominator. I got to look at u substitution. Okay, what could be our u value for number 1? Yeah, 2x plus 3. Okay, it's going to end up being 1 over u, natural log. Okay. Okay, number 2. Like, too many terms in the denominator. We got to look at u substitution. What could be our u value? Entire denominator again. The numerator is encouraging because we know that the derivative of 4x squared will produce a linear term, and that should match and cancel out with that x. Okay, now look at number 3 here. It's also a fraction, but what do you notice here? Yeah, there's only one term in the denominator. This is not a u substitution problem. This is simple enough for us to separate and expand. Okay, it may not be power rule, but it will be independent problems that we don't need u substitution for. Okay, we can split this up. Actually, let's work this out just so we can get that practice in. So I'm literally just going to split this up into 2 problems. So you can just see that, okay, I'm really just dealing with 2 independent problems that have no impact on each other. Get the x's to go away. Okay, maybe I'm going a little overboard by writing out each separate term, but I just want you guys to see that these are 2 separate rules, right? What can I use with the first term? Okay, power rule. Second term. Well, this is simple enough where we don't. Yes, it's 1 over x, which is. Yeah, natural log. That's just natural log. Yeah, so jump directly into our rules here. 2 becomes 2x. The 5 stays, and that's just natural log absolute value of x plus c. Okay. No need for u substitution if there's only one term, one monomial in the denominator. I mean, it could be 5x, could be 7x, but as soon as you introduce like an x plus 3 or x minus 1, then we got to look at something else. Okay. Let me come back to number 4. I want to talk about the other problems before I come back to number 4. So let's look at number 5. Just the first step here. Now, again, you may be looking at this saying, oh, wait, there's only one term in the denominator, but the numerator and denominator are not in the same families of functions, right? We can't merge this together into one term easily. So we really have to explore u substitution. What could be our u value for number 5? Yeah. Anytime that you see parentheses and you're exploring u substitution, that's a good place to start. Again, it's not guaranteed that every parentheses is going to be your u value, but if it's there, at least explore it. At least explore that option. The derivative will produce something involving x, and that should cancel out nicely. Okay. All right, we'll come back to that. Number 6. How would you start this one? Say it again. So the issue with the whole denominator is that if we let this whole denominator be the u value, and if we find the derivative, is it all just going to become 0 or 1? There's going to be some leftover, right? And that leftover is not paired up with anything. So that's a little too much. The entire denominator is a little too much because we need some leftover for the derivative to pair up. Yeah, it's going to be that 1 plus root x. Again, we target the parentheses. We know the root x derivative is not just going to go away to 0. There's going to be a power rule involved, and then that derivative hopefully should be handled by this root x. Okay. Okay, we'll come back and finish that problem. Okay, what I want to focus on is on the back page, the top page, top of the second page. Okay. 7 and 8, we will work through. This is one of the new methods that we learned. So take a look at number 7. Okay, let's go down our list of checklists here. I always want to explore power rule expansion, but look, there's too many terms, right? If it was just x, then I can just separate them out and treat them as individual fractions. But here, that x minus 3 kind of adds that complexity to it. I can't just separate them out into individual parts. Okay, so then use substitution, right? That's our second option. Numerator, degree, if I let the u value be the numerator, I can't easily cancel out with the denominator. It just doesn't work out as nicely. If I let the denominator be the u value, it's not going to pair up nicely and allow the x to go away. So power rule expansion doesn't work. U substitution doesn't work. We have a new method. What problem, what category does this fall under? This is long division, synthetic division. Okay, long division, synthetic division has this particular form to it. Okay, in this case, we can do synthetic division because the degree in the denominator is just easy and low. It's just x to the first power. So you know synthetic division is going to be a good fit, or long division for this matter, because you have multiple terms in the denominator, your degree in the numerator is higher, and synthetic division because the degree is the first power. So let me go through the full steps for synthetic division. We'll work through this problem and then have you guys try number 8 on your own to see if you can replicate that process. Okay, so the first thing we do is we need to find that outer factor. So the way you find that outer factor, you set x minus 3 equal to 0, you solve for x, basically just going to be the opposite sign. So it's just going to be 3. Okay, put that outside a half rectangle. And now for the first row, you're just going to put the coefficient of your dividend, okay? So don't put any variables here, just the coefficients. So for x squared, I'm going to put what? 1. Negative 4x will just be negative 4, and then the 8. Okay, so first thing you do is you always bring the first number down below the line. Okay. Once your number is outside the box, then you can involve the number, the factor that you see outside here. So 3 times 1 is going to be 3. Add. Negative 4 plus 3 is negative 1. Multiply again. Negative 3 times negative 1 is negative 3. Add. And we get 5. Okay, so now we have to assign variables to those coefficients. Remember that you're dividing by x to the first power, so every degree is going to fall by 1. This initially was x squared, so this is going to fall to what? Just x. And everything is going to fall by 1 degree. So this is x, this is a constant, and what do we call this? Remainder. There's a special way that we write the remainder, which is what? Yeah, over the divisor, okay? This is just to indicate that I can't divide any further. I've gone as far as I can go. It's not going to zero out. This is my leftover. Now, keep in mind that this is not the answer. This is just an easier problem for us to find the antiderivative. So we still got to go through the calculus process. But at least these are 3 separate problems. Okay, first term is power rule. Second term is power rule. Third term is just an easy use substitution that if you want to just look to see and understand that it's always going to be natural log, you can just involve that natural log. But technically, you can say that, okay, u is x minus 3, du equals dx, and it's just going to be 5 integral of 1 over u du. Okay. So we go through power rule for the first term. X becomes x squared over 2. What does 1 become? Good. And then the last term, if you can imagine this as 5 times 1 over u, it's just 5 natural log of x minus 3. Okay, so anytime you see a easy problem like this, once you're comfortable, you can just jump directly into understanding that with synthetic division, it's always going to be that last term being natural log. Okay, let's see if we can try number 8. Yes, question? So what's the derivative of x minus 3?
Wait, what?
1. Yeah, so that's why nothing remains. Okay, try number 8. Same process. Okay, but I just want you to practice through that synthetic division process. Get that assign variables to the coefficient, and then apply the antiderivative rule. Every term mostly will be power rule, and the last term will specifically be natural log. Okay, try number 8. Okay, once you assign each of the coefficients, go through that process, bring the first number down, multiply, add, multiply, add. Last term will be your remainder. And just remember that you still got to do power rule. That's not the answer. That's just the beginning point of our problem here. We're basically just simplifying it to the point that we can apply these integral rules. So every term is power rule, and the last term is just going to be a natural log rule. Okay, you guys have homework from 5.5. We got through a big portion of the quiz review. We'll do quiz review worksheet number 2 tomorrow. Wednesday's our quiz, but I'll have a morning review on Wednesday. Have a great day, guys. See you tomorrow. Thank you. Thank you. Thank you. Thank you.
See you, Jay.
See you, Jay.
Thank you. All right. Have a good day. Thank you. Have a good day.